All right, welcome back, everyone. Today we're going to be going over the sample final exam for the department. I'll be going over every single problem um, that's on the sample final. Typically the final exam for this course, it's very similar to the sample final in the nature of the questions that are asked. So if you see a type of question asked on the sample final, then you can expect that type of question to appear on the final exam. Um, it is the departmental policy that if you fail the final exam, you fail the course, even though you may be passing every other every other exam and did all your homework and you were averaging 100. If you fail the final exam, you will fail the course. So please make sure that you are studying as much as you can and preparing as much as you can for to pass this exam. Without further ado, let's begin. So the first question on the sample exam is to compute the derivative dy dx for y equals square root of 5 plus x to the 5 minus 5 minus 5 times the ln of x. So if we're computing this derivative, then remember we could take the derivative by parts. So we could take the derivative of each of these parts independently. So I could do dy dx for radical 5 plus dy dx of x to the 5 over 5, and then plus dy dx for negative 5 times ln of x. Now, the derivative of the square root of 5 is just 0 because it's just a constant, and the derivative of any constant is 0. The derivative of x to the 5 over 5 is just 1 over 5 times the derivative of x to the 5, because it's a constant, we could pull it out. So the derivative of x to the 5 is simply 5x to the 4 by the power rule. And finally, the derivative of negative 5 ln of x is negative 5 times the derivative of ln of x. Remember, ln of 5 is a constant, so again, we could pull it out. And the derivative of ln of x is just 1 over x. So when you put this all together, when you simplify, well, the 0 goes away. If you multiply 1/5 times 5, it's just the same thing as dividing by 5, so the 5's go away. So you get x to the 4th. And then negative 5 times 1 over x is simply negative 5 over x. So this is one of the most important things that you need to know how to do in the exam, taking derivatives. This is a calculus 1 class, so the least that you need to be able to know how to do is to take derivative of functions. And as such, that most of the exam is just taking derivatives. Number 2 is to compute the derivative p prime of y of a function p of y is equal to 2y plus 3 divided by 7y plus 5. Now, notice that this problem, we have a rational function. So this is a rational function, which means that we're dealing with a fraction, and if we're dealing with a fraction, we have to use the quotient rule. And remember what the quotient rule said. So the quotient rule said the following: if we're talking about f of x being the numerator and g of x being the denominator, then we have the following. We have the derivative of the first times the second minus the derivative of the second times the first, and then the bottom times divided by the bottom squared. Okay, so you definitely need to know all of the rules of differentiation, and one of those rules is the quotient rule. So what do we get here? We have let's define what f of x and g of x are, because it will make our work much easier. So here, f of x will say f of y. Actually, we're talking in terms of y. I'll leave the formula the same, but we're talking in terms of y. F of y is going to be 2y plus 3, and g of y is going to be 7y plus 5. So numerator and the denominator. And the derivative of the numerator is simply 2. The derivative of the denominator is 7. So this is going to be a simple enough derivative once we put it into the formula. Because the formula says f prime, which is in our case 2, times g of x, which is 7y plus 5, minus g prime of y, which is 7, times f of y, which is 2y plus 3, all divided by 7y plus 5 squared. So that's why the quotient rule. And we could simplify this a little bit. We get 14y plus 10 minus 14y minus 14y minus 21 divided by 7y plus 5 squared. I'm not gonna expand the denominator. I trust that you don't have to do that. The 14y's cancel out, and 10 minus 21 is negative 11 last time I checked. So we have negative 11 divided by 7y plus 5 squared. You could expand this, but chances are that because your exam is going to be either on my lab or in person, if it's in person, I accept this as an answer. If it's on my lab, then simply answer the way that my lab wants you to answer. It will tell you which way you want it to answer. Now, before we move on from this problem, I'm just going to rewrite it again because I want to make a point. The problem was 2y plus 3 divided by 7y plus 5, and we used the quotient rule to solve this. We could have also used the chain rule if we rewrote the problem like this. Just simply bring the denominator to the top and write it with a negative exponent, and then you could solve this problem by using the product rule and the chain rule. So you have a product of two things, so you will have to use the product rule, and then with the second expression here, you will have to use the chain rule. And you could solve the problem this way if you somehow forget the quotient rule. The third problem on the final exam is the following. It's one of the most important problems that we did earlier in the terms, which is to write down an equation of a tangent line to the graph of y equals 1 plus 2e to the x at the point where x is equal to 0. The first thing that I will do is, first of all, rewrite my function given, so it's 1 plus 2e to the x. The second thing that I will do is to figure out what happens when x is actually equal to 0. So if I plug in 0 for x, I have 1 plus 2 times e to the 0 power. Well, e to the 0 is 1, because anything to the 0 power except for 0 is 1. So we'll have 1 plus 2 times 1 here, which means that y is equal to 3. So we're dealing with the point 0, 3. 0 for the x-axis and 3 for the y-axis. Okay, so that's the first thing that I would like to get out of the way, because I will eventually need this to solve for the tangent line, to write down the equation of the tangent line. So might as well get it out of the way. Second thing that I will do is to simply take the derivative. So if we take the derivative of this function, or this equation, we got the derivative of y is y prime is equal to the derivative of 1, which is 0, plus 2e to the x. Well, it's just going to be 2 times e to the x, because remember, by the constant multiple rule, we just multiply times the derivative of the function, but the derivative of e to the x is just e to the x. So the derivative of 1 plus 2e to the x is simply 2e to the x. The constant goes away. Now, to write down the equation of a line, we have to find out the slope of the tangent line. So remember, a line is y equals mx plus b. That's how we write a standard form of a line. To find m for the tangent line, we need to find out what the slope of the tangent line is at the point x equals 0. But because we have the derivative, we just simply plug in 0 into the derivative, and that will give us what the slope is. Now it's going to be 2 times 1, which is 2, by the same basis as before. So we have that m, or the slope of the tangent line, is 2. Okay, remember, this is something that was very important in the beginning of the course and still is important until now. The derivative gives us the slope of the tangent line at a particular point. Okay, it gives us just the instantaneous rate of change at a particular point. So now that we have the slope and we have our point, we could simply write down the equation of the line. You could use y equals mx plus b if you like using it. I don't like using it because sometimes it is not easy to find the y-intercept. We actually have the y-intercept here, so this is easy to write. It's just 2x plus 3. But if you don't have the y-intercept, let's say this was like 1, 3 instead of 0, 3, then this will definitely be a little bit more challenging to use. So I always recommend using the slope point formula, which is y minus y1 is equal to m times x minus x1. And if you do it, so y1 here is 3, so minus 3 is equal to 2 times x minus 0, because the x was 0. So you'll see that we get the same solution. So we have y minus 3 is equal to 2x, and then when you move the 3 to the other side, you get 2x plus 3. So we get the same solution. This was much faster, obviously, because I had the point, I had the y-intercept for my point. But if I didn't have, again, the y-intercept as my point, if I had some other point like 27,5, then the slope point formula is a bit easier than the slope intercept formula. In any case, this you definitely should expect a problem about writing down the equation of the tangent line, because that's one of the main ideas of this course. So you need to remember that the tangent line, the slope of the tangent line is given by the derivative evaluated at the point given, and you need to remember how to write down the equation of a line, and obviously you need to know how to take derivatives. Alright, so let's move on to question number 4. Okay, so we have to determine the slope of the tangent line to the graph of the equation. Okay, so let's determine the slope of the tangent line to the graph of the equation. (5x squared plus 3y squared plus xy is equal to 15 at the point -1, 2. Now, for this particular problem, you need to notice a few things. Number one, this problem has x's and y's all on one side. Notice that there's a y square and there's an x times y, so it's going to be very difficult to actually factor this and move things to one side and the other and just solve for y. When you have something like this, it's just best to simply take the derivative implicitly and then, you know, work out the actual slope for the line and so on. Luckily here we don't have to find the y value of the point, because it's the coordinate is given to us completely with x and y. So what we can do is simply start by taking the derivative. So again, as I mentioned, we're going to take the derivative implicitly, and if you don't remember, what that meant is that we take the derivative for x with respect to x and for y with respect to y, but whenever we took a derivative for y, we also added y prime or dy dx. I could choose either one. I will choose to go with y primes. Sometimes that makes my life easier. Sometimes it's less writing. But anyway, let's start with the derivative. So the derivative of 5x squared is 10x. The derivative of 3y squared is 6y times y prime. The derivative of x times y, here you have to remember the product rule, because this is a product of two things. Product rule is the derivative of the first times the second plus the derivative of the second times the first. That's the product rule. So what do we have here? The derivative of the first is just 1. The derivative of 1 is just the derivative of x is just 1, so 1 times y plus the derivative of the second is 1 times y prime, because remember we took the derivative of y, times x. Okay, the derivative of the second is y prime times x. And the derivative of 15 is just 0 because the derivative of any constant is 0. So now that we have taken the derivative, let me simplify a little bit. This is 10x plus 6y y prime plus y plus x y prime is equal to 0. So now I'm going to take every term that does not have a y prime and I'm going to move it to the right side of the equation. So on the left side I'll be left with 6y times y prime plus x times y prime is equal to negative 10x negative y when you move the 10x and the y to the right side. Then I'm going to factor the y prime on the left side because it's common on both terms. So I'll be left with y prime times 6y plus x is equal to negative 10x minus y. And then I'll solve for y prime by dividing both sides by 6y plus x. So I have y prime, and I should really not be using equality here. Y prime is equal to negative 10x minus y is equal to 6y plus x. So now we have found the derivative of our original given problem. And now we have to write, well, we were just told to determine the slope of the tangent line. We could actually find the tangent line as well if we wanted to. So to get the slope, we just have to plug in our x and y into the derivative. So we have negative 1 and 2. There was a point negative 1 and 2 that was given. So I'll just plug in negative 1 for x and 2 for y. So I'm going to have negative 10 times negative 1 minus 2 divided by 6 times 2 plus minus 1. So this is equal to 10 minus 2 divided by 12 minus 1, which is equal to 8 divided by 11. Oh, yeah. Okay, this is good. 8 divided by 11. Now, all I needed to do was find out the slope. But if I wanted to, again, write the equation of the line, then we simply use y minus 2 is equal to 8 over 11 times x plus 1. And, you could simplify that a little bit more. I will leave it like that. But that will be the equation of the line, of the tangent line, passing through that point. Again, you need to remember or review how to take the derivative implicitly, and how to find the derivative implicitly. Okay. All right. Question numero 5 from the sample exam is to compute the derivative dw/dc of the function w equals square root of 1 plus c e to the z. Okay, so here the first thing that I will do is to rewrite it as 1 plus e plus c e to the c to the power 1/2. So that's the first thing I will do. Then notice that you will have to use a chain rule because this is an instance of the general power rule, so we will have to use a chain rule. We will also need to use the product rule here. So there's a product and a chain rule here happening. So let's see what the derivative dw/dc is. So when I take the derivative, remember the 1/2 comes up front, so I have 1/2 times 1 plus z e to the z to the negative 1/2 power because of the general power rule, and by the chain rule we have to multiply by the derivative of the inside, but the derivative of the inside is going to be the derivative of 1, which is 0, plus the derivative of z times e to the z. Well, again, by the product rule we have the derivative of the first times the second, so that means 1 times e to the c plus the derivative of the second times the first, which means e to the c times z. Okay? And we just need to simplify. So I'm going to take this to the denominator because it has a negative exponent. So this is going to be 1 over 2 times square root of 1 plus z e to the z times e to the c, because 1 times e to the c is just e to the c, plus z e to the c. And when we put this all together, this is divided by 1. So when you multiply fractions, you multiply across. So we have 1 times e to the c plus c e to the c is just e to the c plus c e to the c divided by 2 times the square root of 1 plus c e to the c. Here, the important thing to realize, and this may be very difficult if you haven't practiced enough, is to identify that, first of all, this is going to be a chain rule. So here we have chain rule. And then here we have a product rule. And because of that, we get this piece popping out here because of the chain rule and the product rule. So you have to be able to realize that you're dealing with a product and a chain rule, or a chain rule and a quotient rule, or a general power rule, and then a chain rule or a product rule. So all of these things are things that you have to keep an eye out for. They may come up without you even realizing it. Okay, so the first 5 questions on the final exam would be about techniques of taking derivatives. Product rule, quotient rule, chain rule, power rule, general power rule, and the tangent line problem. The next 3 questions will involve something that we did even before we learned how to take derivatives, which is finding limits. So question number 6 is to find the limit of the following. Limit as theta goes to 0 of 3 sine of 4 theta divided by 5 of theta. So we want to find out what that is equal to. Now you may not remember this. I told you that this is a very important theorem in math, and that is the squeeze theorem. We have seen that by using the squeeze theorem, the limit as x goes to 0 of sine of x divided by x was equal to 1. If you don't remember, that's okay. I do suggest that you review this, and this is a special limit. And again, this special limit, you can show it by using the squeeze theorem. There's another special limit, and that is the limit as x goes to 0 of cosine of x over x, and that one is equal to 0. So again, you should remember both of these. They are very important. Now, understanding this will help us solve this problem up here. So the problem that we're given is limit as theta goes to 0 of 3 times sine of 4 theta divided by 5 theta. Now, I have no idea what this limit is equal to yet, but I have many techniques that we have learned throughout the term that we can apply for limits. One of those techniques is the following. The constant multiple rule applies to limits. So I could take out this 3 because it's not affected by theta, and I could take out that 5 as well, so I could take it out. So I could take out the 3 over 5 and multiply times the limit as theta goes to 0 of sine of 4 theta over theta. Now, I'll wave my hands a little bit here, but it turns out that this is actually equal to 4, this limit when you do it. So I'm going to do some hand waving here, and that is because of this rule. So sine of 1x over x as limit of x goes to 0 is 1. Sine of 4 theta over theta as limit goes to 0 is 4. So what we get here is 3 over 5 times 4. Again, this is by the squeeze theorem. You could show that this is true. So we get that the solution to our problem is equal to 12 over 5. Okay? That is why this special limits, limit techniques. Okay. All right. So that's question number 6. The final will include a problem like this, using this special limits, either sine or cosine, or a mixture of the two. So you need to understand how to use them. When you get good at this, when you see something like this, you'll know that it's going to be 3 times whatever's inside divided by this number. But again, this is by using the squeeze theorem. Question number 7 will test another limit technique that you should know. So that is to find the limit of the following. The problem given is limit as x goes to 1 of x squared minus 4x plus 3 divided by x squared minus 1. Now, remember, one of the simplest tools that we have when we evaluate a limit is direct substitution. What direct substitution means is that you take the number that you're limiting to and you plug it in for the variable. If there are no issues with the domain, then whatever you get will be the solution to the limit. Here, because we have a rational function, when we plug in 1 into the denominator, we're going to have 1 squared minus 1. But 1 squared minus 1 is equal to 0, and we cannot divide by 0, so we have a problem. Okay? Because we have a problem, we have to do something different. What should we do? Well, the first thing that I will do is to try to factor this, because there may be some cancellation, and we may be able to use a similar expression that has that actually has a limit as x goes to 1, and is similar enough to this expression such that there are no issues with the denominator. So the denominator is the difference of two perfect squares, and this factors as x minus 1 times x plus 1. The numerator factors as, let's see, two numbers that multiply to 3 but add up to negative 4. It's going to be negative 1 and negative 3, because notice that negative 3 times negative 1 is going to give you plus 3, but negative 1 plus negative 3 is going to give you negative 4. Now, because so long as x minus 1 is not equal to 0, we could cancel the x minus 1s, and we are left with the limit as x goes to 1 of x minus 3 divided by x plus 1. And notice that this limit does not have an issue in the denominator, because when you plug in 1, if you use the plug-in method, it's going to be equal to 1 minus 3 divided by 1 plus 1, which is going to be negative 2 over 2, which is equal to negative 1. So the limit as x goes to 1 of x squared minus 4x plus 3 divided by x squared minus 1 is equal to negative 1. Okay, so this is what we have here. It's a good example. Typically, when you factor a problem like this one of the factors should pop up in the numerator. In a class like Calculus 1, these problems are built that way. So that's a thing to watch out for. The next problem is another limit problem. And it will test yet another technique that we had prior. So it's to find the limit of the following. It's a limit at infinity. So it's limit as x goes to infinity of 6x squared plus 100 divided by 7x squared minus 100. Keep in mind we did two topics that sound similar but are not exactly the same. We found limits at infinity and we found infinite limits. Okay, so this will be an example of a limit at infinity. Yeah, the limit symbol is looking terrible today. Okay, so notice that we're dealing with x squares in the numerator and denominator, and we cannot just wave our hands and cancel them out. That's not allowed. One technique that we had spoken about when doing problems like this is to multiply the numerator and denominator by the biggest variable to the highest exponent that you see in the denominator. So here in the denominator you have x squared. So we're going to multiply the numerator and denominator by 1 over x squared. And that's going to give us limit as x goes to infinity. And instead of 6x squared, we're going to have 6. I'll actually write everything so you can see multiplication. Plus 100 divided by 7x squared minus 100. And what we're doing is we're going to multiply by 1 over x squared each term in the numerator and in the denominator. And what we have here is that, again, so long as x squared is not equal to 0, and we know it's not equal to 0 because the numbers are going up to infinity, we can cancel the x's out here and here. So we get is limit as x goes to infinity now of 6 plus 100 divided by x squared over 7 minus 100 divided by x squared. Now we know how to deal with this type of limits. Why, or how do we know this? Well, notice that this is a constant in the top, so that number is staying the same. This 100 is staying the same, but the bottom is getting bigger and bigger and bigger. At first it's 100 over 1, then 100 over 2, then eventually it's going to be 100 over 100, then 100 over 200, and so on. You're going to have 100 over, let's say, 3,000, and you can see that the fraction as a whole is getting smaller because the denominator is getting bigger and the numerator is staying the same. So when that happens and the denominator stays the same, but when the numerator stays the same but the denominator gets larger, the fraction as a whole becomes smaller. A way to see this is the following: 2 over 3, you know that's 0.67, right? Approximately. Now, if you make, if you leave the numerator the same, hold on, why are you not writing? Okay, that's not good. Alright, I'm having some technical difficulties. Please bear with me.